Okay, let me start with this tensors. We already know what a scalar is. Many times we come across scalars and we discussed about scalars in our previous classes also. Scalars are mathematical entities or mathematical representations which need only a magnitude to describe. If you want to describe a scalar, you need a magnitude. You need only a magnitude, that's enough, right? But when it comes to vectors, magnitude alone is not sufficient to describe a vector, so we need magnitude and a direction also, right? So this is well versed to everyone. Magnitude alone is needed to describe a physical entity, means that we call it as scalar. And the physical entity which requires a magnitude along with a direction to be described, then we name it as vector. Now you just imagine some physical quantity or physical tool, some physical object that requires magnitude and two directions. To describe a physical quantity, if at all you require a magnitude and two directions. There are some cases, and there may be some cases like this also. You may require a magnitude along with three directions. There is possibility that you require a magnitude and four directions to describe some physical entity, right? The common name for all such things, that is tensor. So tensors are the mathematical tools, or you can say mathematical representations or mathematical entities that can be used to describe physical property, any physical system, just like scalar and vector. Then based on the requirement, if it is required only magnitude and a direction, we call the tensor as vector. But if it requires a magnitude and two directions, we have specific name like dyadics. If it requires three directions, we call it as triadics. If it requires four directions, we call it as tetradics. And it goes on. It doesn't end here. It goes on. If any physical system requires magnitude and 5 directions, magnitude and 6 directions, accordingly we have higher order tensors also. Common word you can use like polyadics, P-O-L-Y, poly, many, polyadics, or we call it as tensors of higher orders or higher ranks. So scalars and vectors also become part of the tensors only. So tensor is generalized. It's a generalization, right? And scalars and vectors become the special cases of tensors where vectors require only one direction and scalars require zero direction to be to describe any physical system, right? So tensors are the mathematical tools that can be used to describe a physical system, right, in terms of magnitudes and directions. Based on how many directions are required, we name them. So scalars and vectors are the special cases of tensors. You have any doubt in this? No doubt?
No.
Okay. This dyadics, it's also known as matrices. See, magnitude of two directions, right? They are dyadics and they are in the matrix form. We cannot say all matrices are tensors, but some 3 by 3 matrices which are symmetric, which are Hermitian under certain conditions, those matrices are the tensors which require a magnitude and two directions. Now let's come to the part of the rank of a tensor. Say, to describe some...
Ma'am?
Yes.
I'm sorry, ma'am. Ma'am, what did you say about the matrices? Your voice fluctuated due to network. Could not hear that.
Okay, not all the matrices are tensors. Some matrices, a 3 by 3 matrices, which are symmetric in property and which are Hermitian. Maybe in matrix properties we will study Hermitian matrix. Hermitian matrix, a symmetric Hermitian 3 by 3 matrix, they form tensors of dyadic tensors, which require 2 directions and 1 magnitude for describing physical quantities. This is what I told.
Okay, ma'am.
Okay. Now coming to the part of the rank of tensor. See, first let us start with the scalars. It requires only a magnitude, right? So now how many number of components we require to use this scalar? See, only one, because scalar it is just a number. Any scalar you are going to write a number like a 10 or 12 or something. So only one component is sufficient to describe a scalar. When it comes to vector, how many components we require? For example,
3.
yeah, good. AI plus BJ plus CK. So, a component along I direction, a component along J direction, a component along K direction. We need 3 components in 3 directions each. So, 3 components are required to describe a vector. Similarly, if you go for dyadics, it requires 9 components because it involves 2 directions. And triadics, they need 27 components. And tetradics, they need 81 components. It goes on for higher order tensors also. And I prefer to write these numbers in this format. Can I write like this? 1, I am writing like 3 power 0. Can we write?
Yes, ma'am.
Yes. Same way, I am going to write like this. 3, I am going to write 3 power 1. 9, I am writing 3 square. 27, I am writing 3 cube. 81, I am writing 3 power 4. And it goes on. So, the number of components we require for higher order tensors, they increase in the order of 3, like this 3 power 5, 3 power 6, like this it goes. So this power, the number that comes in the power, that decides the rank of the tensor. So what is the rank of a scalar? It is 0. Whatever the power, whatever number you have in this power, that is the rank of the tensor. So rank 0, rank 0 for scalar and rank 1 for vector and rank 2 for dyadics, rank 3 for triadics, rank 4 for tetradics and 5, 6 goes on. So tensors of any order. Tensors can have many rank. If a tensor has rank 0, it is nothing but a scalar. If a tensor has rank 1, it is nothing but a vector. So far we dealt with scalars and vectors in the previous units, right? And a tensor with rank 2, it is matrix. It is dyadics and they are in the matrix form, right? That we are going to deal in the next unit. Matrices we are going to see in the